This is a worked example for a typical moments question. So we've got a 650 Newton diver standing on a 2 metre long diving board. The board itself weighs 200 Newtons and it's supported as shown. So here's the board. There appears to be a pivot point beneath the board that the board's pushing down on. And then to stop the board rotating, the board's pushing up, and therefore the pivot's pushing down on the bottom end of the board. And the question says, what are the forces at these two pivots here? There's something else in this question that's a bit of a clue as well. It tells us the weight of the board, and that's going to act, assuming it's a uniform board, and if it wasn't they would tell us, that's going to act at the centre of mass or centre of gravity, whichever you prefer. Okay, so I'm going to follow my own advice and I'm going to start by redrawing this as a diagram showing all of the forces. So step number one, I'm going to draw it. So it's basically the same picture, but I'm going to, for convenience, make it a bit longer so I've got a bit more space. I'm going to put this point here and I'm going to label this A so that I can refer to it later. This point here I'm going to label B. I'm not going to bother drawing my diver this time, I'm just going to draw a little box. And what else do we know? We know that the distance from A to B is 0.75 meters. We also know that the weight of the diver is 650 newtons. So I'm going to draw an arrow here, 650 newtons. And we also know the weight of the board is 200 newtons. And that will act in the middle of the board. So I'll draw an arrow down here, 200 newtons, and we can add a little bit more information. Okay, so what else could we add? We can add that, well, A is clearly pushing down, stopping that board rotate, so I'll draw an arrow down here and I'm going to label that RA. It's a resultant force, no it's not, it's a reaction force and it's at point A, so RA. And B must be pushing up on the board. Now I've drawn this badly, so I'm going to do this up here. And I'll call that reaction force B. Now is there anything else I can add? Yes, I can also add that the distance to the middle of the board, if it's a 2 metre long board, must be 1 metre, and the distance between this pivot and where the diver is 2 metres. So that's all of the information we've got, and we've got two unknowns, RA and RB. And we want to find out one of those. So probably the best thing to do is to decide where we're going to take moments from. We can take moments about point A or about point B. I'm just going to go with about point A. The important thing here is that you'll see that by taking moments about A, the force RA is not going to contribute to that moment at all because its distance from A is 0 meters. So that will not be in the equation, and it means that we only have one unknown, and this becomes really simple to solve. Now when I lay these out, I normally try and remember to tell myself what I'm doing, so that if I'm trying to understand a mistake later on, I can go back through it. So I'm going to say that I'm going to take moments about point A. So I'm going to say, right, what are the clockwise moments? So the clockwise moments are going to be 200 newtons times 1 metre. So 200 newtons times 1 metre. And over here we've got the weight of the diver, so 650 newtons times 2 metres. I obviously wouldn't always put the units in this calculation, but I'm just using that for this demonstration. Okay, and by the principle of moments, if this is in equilibrium, all of this will equal the anti-clockwise moments. And the anti-clockwise moments for this one, well, we've got the 650 trying to go clockwise, 200 trying to go clockwise. The only thing going anti-clockwise is this force RB. So it's going to equal RB times 0.75 metres, because the question tells us that's its location. And then you solve that, and I think it comes out at, this is 1,500 Newton meters is going to equal RB times 0.75, and then clearly that should be RB equals 2,000 newtons. So we've solved for RB. Now we need to find RA. And I think the trick here, well, not trick, but the easiest thing to do here is to enter the information you've just worked out into the diagram. So we've got 2,000 newtons here. And at this stage, we don't need to use moments anymore. Because if this is an equilibrium, the forces up are going to equal the forces down. So we've got 2,000 newtons acting upwards, and we've got 650 plus 200 plus RA all acting downwards. So to find the next one, it's really straightforward. Up, we've got 2,000 newtons, and that's going to equal the forces down, which is RA, that's acting down, plus 200 plus 650. And when you solve all of that, therefore RA is going to equal 1,200 newtons. And that's that.